we've all heard it before. The universe is vast. It's big, it's immense, and it stretches beyond comprehension. But do we ever truly understand what that means? When we say something is big, we think of a towering skyscraper or a sprawling city. When we say something is far, we imagine a long drive or a flight across the globe. These measurements are part of our everyday life, things our minds were built to grasp, to measure, to understand. But what happens when we step outside of the familiar and into the realm of the infinite? What happens when we try to comprehend the true scale of the universe? The truth is, our minds weren't made for this kind of scale. They weren't designed to process distances that stretch into the millions and billions of kilometers. Think of how small our everyday measurements are compared to the cosmos. We can walk a few kilometers without breaking a sweat, but that's a fraction of the distance between the Earth and the Moon. When we think of distances on Earth, we often use terms like close or far based on the movements we make in our daily lives. But in the universe, those terms barely hold any meaning. The scale of the universe is so large that it begins to mock our attempts to measure it. Distance, as we know it, stops making sense when we scale up to cosmic dimensions. Imagine trying to measure the Pacific Ocean with a teaspoon. Such is the task at hand when we try to make sense of the universe's true enormity. Yet, we try, we measure, we quantify, we calculate, and somehow, in the process, we start to make sense of it, even if only in the smallest way. The journey through this video isn't about trying to grasp it all. It's not about finding answers that can fit neatly into our understanding of time and space. Instead, think of it as a slow, meditative journey outward, afloat through the immensity of the cosmos. It's not about understanding, but about appreciating the vastness. We may never fully comprehend the size of the universe, but we can be humbled and amazed that we, as humans, get to witness it at all. In the end, the biggest revelation might be that we don't need to understand everything. Sometimes, just the act of wondering is enough to make us feel our place in this grand tapestry. We live in a world of familiar distances. A walk to the corner store, a car ride to the next city, a plane flight across an ocean. These are the distances that define our world. They're manageable, tangible, measurable. You can feel them, you can experience them, and you can even predict them with precision. But what happens when you try to scale up? When you attempt to move beyond the confines of Earth's surface and into the cosmos? Those same measurements begin to fall apart. Let's start with something close to home. The distance from the Earth to the Moon, a mere 384,000 kilometers. For some, that number might sound huge. It's almost 10 times the circumference of our planet, a vast distance by any human measure. But the moment you step outside Earth's atmosphere and begin looking up, the Moon's distance starts to feel manageable. After all, we've sent astronauts there. We've walked on its surface. It's within our grasp in ways that other places in the cosmos will never be. Now, consider the distance to our Sun. 150 million kilometers. That's a distance so large that it's hard to fully appreciate with the simple numbers we use in every day. Life, it's 400 times farther than the Moon. And the moment you start thinking about it, you realize how quickly far begins to lose its meaning. Sunlight, traveling at the fastest speed in the universe, takes over 8 minutes to reach Earth. If you were standing on the Sun, it would take over 8 minutes before you could even see the light of your own hand held out. In the world of astronomy, this distance is referred to as one astronomical unit, a unit specifically created to measure distances within our solar system. This is our first tool for quantifying the vastness of space. And it's a handy tool, making the immensity of the solar system a bit more manageable. Mercury orbits the Sun at about 0.4 astronomical units. Jupiter sits around 5.2 astronomical units, and Neptune, our solar system's outermost planet, resides nearly 30 astronomical units from the Sun. These numbers help us bring some structure to the vast distances between celestial bodies. But as we'll soon see, these numbers become even more abstract when we venture beyond the confines of our solar system. The distance between objects within the solar system is simply the beginning. The moment we start to talk about other stars, other galaxies, those manageable distances start to feel like a distant memory. When you're looking at a star, you're not just looking at a distant object, you're looking into the past. Light takes time to travel, and the farther away an object is, the longer it takes for its light to reach us. Now that we've grasped the vastness within our solar system, it's time to stretch our imagination even further. Enter the light year, a unit that astronomers use to describe the immense distances between stars and galaxies. But a light year isn't a measure of time, as the name might suggest. It's a measure of distance. More specifically, it's the distance that light can travel in 1 year, moving at a speed of about 300,000 kilometers per second. Let's break that down. In just 1 second, light can circle the Earth 7 times. That's how fast it moves. So, imagine how far light travels in an entire year. It covers almost 10 trillion kilometers in that time. A single light year is nearly unimaginable, and yet, it's the most efficient way to measure the vast spaces between stars. To give you a sense of scale, let's take the nearest star to Earth outside of our Sun, Proxima Centauri. This star, a faint red dwarf, is part of the Alpha Centauri system, and it's located over 4 light-years away. That's over 40 trillion kilometers, an unimaginable distance. If you were to travel there aboard a spacecraft, even one traveling at more than 60,000 kilometers per hour, it would take you over 70,000 years to reach it. The concept of a light year is not just about distance. It also introduces the idea that when we look at distant stars, we are looking into the past. Light from Proxima Centauri, for instance, takes over 4 years to reach us. If something were to happen to that star today, say, it exploded, we wouldn't know about it until 4 years later. In this way, the light year becomes a time machine. Every time we look into the night sky, we're not just seeing the stars as they are right now. We're seeing them as they were when that light first left their surface. The farther we look, the farther back in time we're peering, watching the universe unfold before us. The stars we see tonight are echoes of events that happened in the past, some of them millions or even billions of years ago. And that's just the beginning. The more we venture outward, the more these time machines begin to show us history, a history we can barely comprehend. Our eyes are constantly being flooded with light from the past, a past so vast that we may never fully understand it. As we venture deeper into the cosmos, the concepts of time and space become increasingly intertwined. This is where things get fascinating and, admittedly, a little strange. Imagine looking up at the moon. The light you're seeing today left the moon just over 1 second ago. Now, think about the sun. The light that bathes you on a warm afternoon actually left the sun about 8 minutes ago. And when you look up at distant stars, such as Sirius, the brightest star in the night sky, that light took about 8.5 years to reach you. But here's where it gets even more mind-bending. When you gaze at distant galaxies like Andromeda, the light we see tonight, left that galaxy over 2.5 million years ago. That's not a typo. You're looking at a galaxy as it appeared long before humans walked the Earth, before our ancestors even evolved into Homo sapiens. You're not just looking at light. You're looking at a moment in time, preserved and stretched across vast distances. This concept of looking into the past introduces something that, in many ways, makes space feel like a time machine. Every light beam that travels to us carries with it a snapshot of history. In a way, the universe doesn't just exist out there, it's unfolding in reverse as we look at it. We're not merely observing the present, we're watching history in motion, a past that stretches back through eons. And all of it is just a little bit out of reach. Here's an example to illustrate this even further. Imagine a supernova. When a massive star reaches the end of its life, it explodes, sending out shockwaves of energy and matter into space. If a star in a faraway galaxy were to explode, it could take millions of years for the light from that explosion to reach us. By the time we see the explosion, that star may have already long since turned into a black hole or faded from existence. The light we're seeing is an echo of something that happened long ago, and in the case of the most distant galaxies, that light could have been emitted when the universe was still in its infancy. What makes this even more curious is that the farther away a galaxy is, the older the light that reaches us. The further back we peer into space, the further back we are looking in time. What's even more mind-boggling is that light itself is our only connection to the past. Without it, we would have no idea what's happening far beyond our world. So, every time we look up at the stars, we are gazing into the vast, complex history of the universe, an archive that stretches all the way back to the very beginnings of time itself. As we stretch our minds further into the cosmos, the units we use to measure space start to grow even more specialized. We've already encountered the astronomical unit O and the light year, both of which help us understand the vast distances within and beyond our solar system. But as we venture farther, even these measurements start to seem too small to describe the scale of the universe. This is where the parsek comes into play. A parsek is a unit that's based on trigonometry and specifically measures the distance. Two stars using parallax, the apparent shift in position of a star, as seen from Earth's changing position around the Sun. 1 parsec is roughly equal to 3.26 light-years. While this might sound a bit abstract, it's a crucial unit in astronomy, especially when mapping out the stars and galaxies beyond our own. For example, Proxima Centauri, the nearest star to Earth besides the Sun, is about 1.3 parsecs away. Using parsecs instead of light years allows astronomers to deal with much smaller numbers when calculating distances within our galaxy. However, in practice, most people find light years more intuitive. After all, we're used to thinking of distances in terms of time, and light years give us a sense of how far light can travel in a year, which brings an almost poetic quality to the idea of space. The farther away an object is, the older the light we're seeing, and with each light year, we're looking into the past. Still, no matter which unit we use, parsecs, or light years, our minds struggle to process the vastness they represent. While these units help to quantify the unimaginable, they don't truly translate to our everyday experiences. These are numbers that slip through our fingers, escaping our ability to grasp them fully. To put it simply, the more we scale up, the less those numbers feel real. Billions of kilometers or millions of light years sound impressive, but they don't hold the weight that a simple 10 kilometers might have. When we think about walking down the street, and that's the crux of the issue, These numbers, as mind-boggling as they are, can never make us truly feel the scale of the universe. What they do instead is help us stretch our perception, forcing us to imagine distances that go beyond our comprehension, even if we can't quite feel them. These cosmic units serve as bridges between the finite world we know and the infinite expanse that lies beyond our understanding. Now that we've begun to wrap our heads around the vastness of space through measurements like light years and parsecs, we must turn our attention to a concept that serves as both a limit and a guide: the speed of light. It's an unshakable, constant, a cosmic speed limit that governs everything in the universe. No matter how powerful our rockets or how advanced our technology becomes, we will never be able to exceed the speed at which light travels: 299,792 kilometers per second. Think about that speed for a moment. In the blink of an eye, light can travel around the Earth 7 times. It can zip from one side of our planet to the other in mere seconds. But out there in the great expanse of space, even at that mind-boggling speed, it takes light time to reach us. In fact, it takes 8 minutes for light to travel from the sun to Earth, and even longer for it to reach distant stars. The speed of light is not just a measure of how fast light moves. It's fundamental to how the universe itself operates. In fact, Einstein's theory of relativity, one of the cornerstones of modern physics, is built on this constant. His famous equation, E equals mc, where c represents the speed of light, shows how energy and mass are related. The speed of light is woven into the very fabric of the universe. It dictates not only the speed of objects in motion, but the very nature of space and time. But here's where things get particularly strange. While the speed of light may seem like a simple number, it has far-reaching implications, especially when we start looking at time and distance on cosmic scales. Since nothing can move faster than light, and light itself takes time to travel, we are, in a sense, always looking into the past. A distant star might seem to shine brightly tonight, but the light we're seeing left that star years, centuries, or even millennia ago. So, in a way, every time we look into the sky, we are watching an ancient time capsule of light from a different moment in the universe's history. This is what makes the speed of light so deeply fascinating and humbling. It is the ultimate cosmic rule. It doesn't bend for anyone or anything. No matter where you are in the universe, whether you're at the farthest reaches of space or standing right here on Earth, you will always measure light speed in exactly the same way. There are no exceptions. It's the one constant we can rely on in a universe where everything else is relative and constantly changing. And yet, despite its steadfastness, the speed of light adds a layer of strangeness to our perception of time. In a universe governed by relativity, time and space are not fixed. They stretch and bend in response to gravity and motion, influenced by the very speed of light itself. This means that our experience of time is relative dependent on where we are and how fast we're moving. The further you travel through space, or the closer you get to a massive object like a black hole, the more time begins to warp. In the end, the speed of light serves as both a limit and a doorway to the strange and wondrous fabric of the cosmos. As we dive deeper into the mysteries of the universe, the relationship between light and time becomes ever more intriguing. The speed of light isn't just a constant, it's also the thread that connects time and space. This thread, however, doesn't always behave in ways we might expect. You see, light and time aren't entirely separate in the vastness of the cosmos. When we talk about light years or distances in terms of light, We're not only talking about how far light travels, but also about how long it takes for that light to reach us. Imagine standing outside at night, gazing at the sky. Every star you see, every distant smudge of light, represents a snapshot of the past, a moment frozen in time. When you look at the moon, the light you see left it about 1 second ago. When you look at the sun, the light that warms your skin left it over 8 minutes ago. But as you look farther into the distance, the light you see has traveled through more time and space, bringing with it a message from a distant past. The stars are not the present. They are time machines, carrying us back to moments long gone. This time illusion deepens as we look beyond our solar system. The light from Sirius, the brightest star in our night sky, takes over 8 years to reach Earth. And when we look at galaxies like Andromeda, that light is millions of years old. So, when we peer into the night sky, we're not just looking at the physical space out there. We're looking at time unfolding in reverse. We are not only seeing where things are, but when they were. And the farther we look, the further back we go. But here's the catch. Time, just like space, is relative. The farther you are from a massive object like a star or a planet, the more time behaves differently. If you were standing near a black hole, for example, time would slow down for you relative to someone far away from it. This is called time dilation, and it's a concept that might sound like science fiction, but it's very much grounded in the theory of relativity. The speed of light plays a crucial role in this phenomenon, bending both time and space in ways we're still trying to understand. It's mind-boggling when you really think about it. Light doesn't just carry information about the space we see, it carries information about the time that space once occupied. Every photon of light that reaches our eyes is a messenger from the past. It's like looking at a photograph from a long-forgotten event, one that was taken in the past, but which, because of the speed of light, arrives only now. In the present, even as we try to measure distances, we are also measuring time. The light from distant galaxies has been traveling for billions of years. When we look at it, we are looking not just at where that galaxy is, but at where it was. We're seeing it as it was millions or billions of years ago, long before the Earth or even our sun existed. So, the farther we look, the more we understand that the universe is not just a space we occupy, but a flowing, ever-changing narrative told in light. Now that we've explored the relationship between light and time, let's dive into the fascinating physics behind how light travels through the vast expanses of space. Light, moving at the speed of about 300,000 kilometers per second, may seem almost instantaneous in our everyday world, but out in the universe, that speed is a reminder of just how immense the distances are. To understand how light shapes our view of the cosmos, it's essential to consider the scale of the universe and how it stretches time and space. At the heart of this concept lies the speed of light's interaction with space itself. It takes time for light to travel across the distances between stars, galaxies, and the farthest reaches of the universe. The farther away something is, the longer it takes for light to reach us, and this time lag gives us a glimpse into the past. But it's not just time that's stretched, it's the very fabric of space itself that light must cross. This stretching, called cosmic expansion, is a key factor in how the universe is growing over time. Take the example of the cosmic microwave background, CMB, the faint glow left over from the Big Bang. This light, emitted roughly 380,000 years after the birth of the universe, is the oldest light we can observe. It represents the earliest moments of the universe, long before stars or galaxies even existed. The CMB is a snapshot of the universe as it was, trapped in time, traveling through space, and arriving at us after a journey of over 13.8 billion years. But even more curious is what happens when light travels through the expanding universe. The farther light travels, the more stretched out its wavelengths become. As a result, the light we see from distant galaxies is often redshifted, meaning it is stretched into longer wavelengths, pushing it toward the red end of the spectrum. This redshift is a direct result of the expansion of space itself, and it's one of the most important tools astronomers use to measure the rate at which the universe is expanding. Yet, it's not just the distance that's mind-boggling, it's the fact that we're not just looking at space, but at history. When you observe a distant star, galaxy, or quasar, you are witnessing it as it was when the light first began its journey toward us. The farther back we look, the older the light and the older the story it tells. This concept of looking back in time is one of the most humbling aspects of astronomy. We are literally seeing the universe in reverse, like flipping through the pages of an ancient book, whose ink is still drying as we turn the pages. The sheer scale of this journey is difficult to grasp. If you were to travel across the universe at the speed of light, it would take you over 4 years just to reach the nearest star, Proxima Centauri. But in the case of galaxies far beyond even light, the fastest thing in the universe struggles to cross the gap. Galaxies that are millions of light years away still appear to us in their ancient form, and it takes tens of millions of years for their light to travel to us. We are constantly looking at the universe as it was watching history unfold before us, 1 light year at a time. Yet, despite the incredible distance that light must travel, it remains the bridge that connects us to the cosmos. Every photon, every beam of light that travels across space, carries with it not just information about where it's come from, but also about when it was sent out into the universe. It's as if we're all standing in the dark, but each flicker of light that reaches us is a memory, a snapshot of the universe's distant past, pulling us closer to a time and place far beyond our immediate comprehension. As we journey further outward from Earth, we begin to encounter the vast emptiness that exists between the objects in our solar system. The solar system, with its planets, moons, and distant icy bodies, often evokes an image of a bustling neighborhood. Yet, in reality, it is more like a lonely desert, sparsely populated with cosmic islands scattered across unimaginable distances. To truly grasp this, let's begin by considering the space between the Earth and the Moon. The Moon orbits Earth at an average distance of about 384,000 kilometers. In everyday terms, that's a considerable distance. Yet, in cosmic terms, it's practically in our backyard. If you were to travel from Earth to the Moon at typical commercial flight speeds, it would take you just a few hours. But here's the kicker. You could fit every planet of our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune between Earth and the Moon, with space left to spare. It's hard to imagine, but the vast majority of our solar system is empty space, and the distances between celestial bodies are far greater than we might expect. Let's take the next step and consider the Earth-Sun distance, 150 million kilometers. It's roughly 400 times farther than the Moon, and yet this distance becomes even more difficult to comprehend. To drive to the Sun at 100 kilometers per hour without stopping would take you over 170 years to reach it. The Sun is so far away that it takes light 8 minutes and 20 seconds to reach Earth. Every time we feel sunlight warming our skin, we are experiencing a moment from the past. The sunlight we see today left the sun when humanity was still brushing its teeth, and the warmth we feel was part of a journey that began long before we even woke up. But the sun is not just a singular point of light in the sky. It is at the center of our entire solar system, and around it, the planets orbit in a delicate gravitational dance. As we move further out, the distances between these planets grow exponentially. Mercury, the closest planet to the Sun, is at about 0.4 astronomical units from the Sun. Venus orbits at 0.7 astronomical units, while Earth sits at 1 astronomical unit. By the time we reach Jupiter, we're at 5.2 astronomical units, and Neptune, at the farthest reaches, is about 30 astronomical units from the Sun. But even this doesn't capture the true vastness of the solar system. The outer edges of the solar system, where the Kuiper belt and the Oort cloud exist, are so distant that even our fastest spacecraft would take centuries to reach them. The Oort cloud, a theorized sphere of icy objects that encircles the Sun, could extend out as far as 100,000 astronomical units, or over 1.5 light-years. This is the true edge of the Sun's gravitational influence, though it remains largely unseen and unexplored. The distances between planets, asteroids, and comets are so immense that they make the solar system feel almost empty. Even the asteroid belt, which is often imagined as a chaotic collection of rocks, is mostly empty space. If you were standing on one of those asteroids, you'd likely see nothing around you, perhaps just one distant dot in the dark, or maybe even complete emptiness. Yet, despite all this space, the solar system is still remarkably busy. Planets orbit in their quiet, elliptical paths. Comets from the outer reaches periodically return, and light continues to stream outward in every direction, carrying with it the warmth and energy of the Sun. Even in the vast emptiness of space, there's an invisible rhythm, a cosmic beat that keeps everything moving, keeps everything in place. As we venture further out into the outer reaches of our solar system, we arrive at the mysterious and largely unexplored Oort cloud. Imagine the Oort cloud as a vast spherical shell of icy objects that surrounds the solar system like a faint, distant halo. It extends far beyond Neptune, at the very limits of the Sun's gravitational influence. The Oort cloud is believed to be the source of long-period comets, those that take hundreds or even thousands of years to complete their orbit around the Sun. Although the Oort cloud itself has never been directly observed, astronomers have inferred its existence through the behavior of comets that appear from the farthest reaches of the solar system. These comets, which occasionally swing in from the outermost fringes of space, provide evidence of an immense region of icy bodies, many of which have remained untouched since the early days of the solar system. To give you a sense of scale, consider this: the Oort cloud is thought to extend anywhere from 2,000 to 100,000 astronomical units. From the Sun, the distance from Earth to the Oort cloud is so vast that even the fastest spacecraft we've ever built would take thousands of years to reach it. To put it in perspective, Voyager 1, currently the farthest human-made object from Earth, is about 150 astronomical units from the Sun, far from the edge of the Oort cloud, and it's been traveling through space for more than 40 years, beyond the Oort cloud. The solar system continues to extend into a cold, empty region of space where objects are so distant and so spread out that it feels as if the Sun's influence is almost a memory. But the solar system's outermost boundaries are not where the story ends. In fact, beyond the known reaches of our Sun's gravitational pull, there may still be vast hidden territories waiting to be explored. One of the most intriguing aspects of space is that, despite all we've discovered, much of it remains uncharted. The solar system, as vast as it is only a tiny speck in the grand scheme of the universe. The Oort cloud marks the furthest known boundary of the sun's influence, but there may be regions even farther out, some of which might never be reachable by our current technology. But even as we push the boundaries of our solar system, the vast emptiness beyond remains largely a mystery. The universe is vast beyond imagination, and as we send probes and spacecraft into the unknown, we are slowly piecing together a picture of this strange and beautiful wilderness. Voyager 1, now beyond the reach of any other human spacecraft, is our greatest messenger, carrying the sounds and images of Earth on its long journey into the dark. It is a symbol of our ambition to explore, to stretch the limits of what we know and, in the process, to glimpse the incomprehensible vastness of the universe beyond. Now that we've explored the outer edges of our solar system, let's take a monumental leap outward and enter the galaxy, the Milky Way. The Milky Way is a spiral galaxy, a sprawling city of stars, gas, dust, and dark matter that stretches across an enormous expanse. This is the galactic neighborhood where our solar system resides, a region so vast and so filled with celestial wonders that it seems to dwarf our humble place within it. To truly comprehend the size of the Milky Way, we need to step beyond our solar system and zoom out to a galactic scale. The Milky Way is about 100,000 light-years across, and it contains an estimated 200 to 400 billion stars. Our own sun is just one of those stars, and it resides in the Orion Arm, a relatively quiet spiral arm of the galaxy. The sun is not at the center of this vast cosmic city, but it's certainly not on the edge either. We live in a peaceful suburb of the Milky Way, a place where life had the time and space to evolve. At the heart of the Milky Way, things get much more chaotic. The center is a dense region filled with stars, gas clouds, and, most notably, a supermassive black hole known as Sagittarius A*. This black hole is millions of times more massive than our sun, and its gravitational pull influences everything around it. Stars orbit the black hole at incredible speeds, and gas clouds swirl in violent orbits, creating a chaotic, energetic environment. But out here, in our corner of the galaxy, the pace is much slower, much quieter. It's a good thing, too. If our solar system were any closer to the center, life as we know it may not have had the opportunity to develop. Despite the vast size of the Milky Way, we are not alone in our region of the universe. The Milky Way is part of a group of galaxies called the Local Group. The Local Group consists of about 50 galaxies, some large and luminous, others small and faint. Two of the most prominent members of the Local Group are the Milky Way and Andromeda, two spiral galaxies locked in a slow, inevitable cosmic dance. The distance between these two galaxies is about 2.5 million light-years, and although that may seem incredibly vast in galactic terms, that's relatively close. Andromeda is on a collision course with the Milky Way, and in 4 billion years, they will merge, transforming the night sky into a breathtaking show of cosmic fireworks. But despite all the motion and activity, the Milky Way remains largely unchanged on human timescales. The stars in our night sky, for instance, may seem to be fixed in place, but they are all moving just very, very slowly. If we could see the stars through the lens of millions of years, we would witness them moving, orbiting the center of the galaxy in a slow and graceful cosmic dance. The Milky Way, like all galaxies, is constantly in motion, carried by gravity and the forces of cosmic evolution. It's humbling to think about the sheer scale of the Milky Way, even though we live in a relatively quiet and stable part of it. The galaxy itself is a vast, bustling city of stars. Yet, despite its immensity, we are barely more than a dot on its sprawling canvas. Our sun, Earth, and everything we know are just a tiny speck in the grand scheme of the galaxy. And that is only the beginning, because the Milky Way is not a solitary island in space. It is part of an even larger, interconnected web of galaxies. Now that we've glimpsed the vastness of the Milky Way, let's zoom in a bit further to examine the movement of our own solar system within this gigantic structure. While it may seem like the stars in the night sky are frozen in place, nothing could be further from the truth. Everything in the galaxy is in motion, and this includes our very own solar system. Our solar system, along with the entire Orion arm of the Milky Way, is orbiting the galactic center, where the supermassive black hole Sagittarius A** resides. The motion of our solar system is not a leisurely stroll, it's a high-speed orbit around the center of the galaxy. The Sun is traveling at an astounding speed of about 828,000 kilometers per hour. This speed is fast enough to circle the Earth more than 20 times in a single hour. Yet, even at that incredible velocity, it still takes the Sun about 225 million years to complete one full orbit around the galactic center. This journey is referred to as a galactic year, and it's a reminder of just how vast our galaxy is. Now, imagine that. One complete orbit of the Sun around the Milky Way's center takes 225 million years. For perspective, this means that our solar system has only completed about 20 orbits since the Sun first formed about 4.6 billion years ago. That's right, while we often think of time as a linear progression, the motions of the galaxy remind us that time, on a galactic scale, moves at an entirely different pace. But even though the galaxy is constantly moving, from our vantage point here on Earth, it often feels like the stars in the sky are fixed, almost unchanging. Of course, we know this isn't true. If we could somehow observe the sky over millions of years, we would see the stars tracing complex, graceful arcs across the night sky, drawn by the motion of the Milky Way itself. The Orion arm, where we live, is not a permanent home. In millions of years, our position within the galaxy will be very different. Stars that seem familiar to us now will have shifted their positions, and constellations will look different. But, as it stands, we are comfortably nestled in a relatively stable region of the Milky Way. This stability has been crucial for the development of life on Earth. The vast distances between stars, combined with the orderly motion of the solar system, create an environment that's peaceful and conducive to life as we know it. If our solar system were closer to the galactic core, it would be a very different story. The intense gravitational forces and frequent supernova in that region would make it incredibly difficult for life to take hold. It's this delicate balance, this cosmic choreography, that allows us to live and thrive in the solar system. Yet, as we continue to orbit the galactic center, we can't help but feel a sense of wonder at the sheer scale and motion of the galaxy around us. We are part of a system that's moving at unimaginable speeds, and yet, here we are, looking up at the stars and wondering about our place in this immense universe. As we stand on Earth, observing the stars above, we often imagine them to be stationary, locked in place in the fabric of space. But in truth, the stars we see are all part of something far grander, a constantly shifting, ever-evolving cosmic dance. This dance is not limited to the stars within the Milky Way alone. It includes interactions with other galaxies, especially our neighbor, the Andromeda Galaxy. Andromeda, or M31, is our nearest large galactic neighbor. It is a massive spiral galaxy, even larger than the Milky Way, containing more than 1 trillion stars. And despite the vast distance between us, about 2.5 million light-years, Andromeda and the Milky Way are on a collision course. In about 4 billion years, these two galaxies will collide. But don't be alarmed. While this may sound catastrophic, the collision will not be as dramatic as it might seem. Galaxies are mostly empty space. Stars are separated by such vast distances that even when two galaxies collide, the stars themselves will not crash into each other. Instead, their gravitational forces will pull the galaxies closer, causing their shapes to distort. The collision will trigger immense star formation as gas clouds in both galaxies collide, compressing and igniting new stars. Eventually, the two galaxies will merge into a single, larger galaxy, likely an elliptical galaxy, sometimes playfully referred to as milky, a blend of the names Milky Way and Andromeda. But even though the collision will not result in catastrophic star collisions, the gravitational interactions between the two galaxies will dramatically reshape the night sky. Stars from both galaxies will intermingle, and the once familiar view of the Milky Way will be altered. The spiral arms we currently see in the Milky Way may no longer be there. Instead, we'll likely witness a vast elliptical structure formed. From the merger, this galactic collision is just one example of how galaxies interact. While this event is billions of years away, it serves as a reminder of the dynamic nature of the universe. Galaxies do not simply exist as isolated entities. They are constantly in motion, being pulled and shaped by the forces of gravity. The universe is full of such cosmic interactions, some of which take place on timescales far beyond our lifetimes. Yet, even in the quiet expanse of space, these cosmic events are happening every moment, changing the very fabric of the universe around us. Andromeda and the Milky Way may be on a slow collision course, but they are far from being the only galaxies in the universe that will collide. In fact, the universe is a cosmic web of galaxies interacting with each other, merging and evolving. Our local group of galaxies is just a small part of this ongoing process, and while the universe may seem like a vast and quiet place, it is full of motion and interaction. Galaxies are constantly in flux, reshaping one another in a dance that stretches across billions of years. As we look up at the night sky, we may not see these distant galaxies colliding in our lifetimes, but the knowledge that we live in a universe of perpetual change, where galaxies like Andromeda are destined to collide with our own, adds a layer of wonder to our understanding of space. This collision is not a distant threat, but a future event that will forever reshape our galaxy, creating a new cosmic reality. Now that we've ventured into the complex interactions between galaxies, it's time to zoom out even further and explore the grand scale of the universe itself. The Milky Way, Andromeda, and their galactic neighbors are just small components in the larger cosmic web, a vast structure that connects galaxies across the universe. But these galaxies don't exist in isolation. They are part of larger clusters, superclusters, and filaments that make up some of the largest structures in the known universe. Let's begin with the idea of superclusters, enormous regions of space where galaxy clusters are grouped together by the gravitational pull of dark matter. One of the most well-known superclusters is the Laniakea supercluster, which stretches over 500 million light-years across and contains about 100,000 galaxies. Within the Laniakea supercluster lies our own Milky Way galaxy, as well as its neighbors, including Andromeda. This supercluster is part of a larger cosmic web, a structure so vast that it defies human comprehension. If the universe were a piece of fabric, these superclusters would be the dense patches of material, while the vast stretches between them would be the empty spaces. This cosmic web forms intricate patterns, with galaxies, stars, and dark matter connected by massive filaments of matter. These filaments stretch across the universe, linking galaxies in a sprawling web, and in between these filaments there are enormous voids, regions of space where little matter exists, and where galaxies are separated by vast distances. These voids are not empty in the strictest sense, but they are regions where very few galaxies reside. One of the largest known structures in the universe is the Sloan Great Wall, a colossal supercluster that stretches over 1.3 billion light-years across. Yet even this structure is not the largest. There are hints of even larger structures, such as the Hercules Corona Borealis Great Wall, a vast galactic wall whose true scale challenges our current understanding of cosmology. These structures are so large, they almost defy logic. They seem to stretch beyond the limits of the universe we thought we knew. As mind-boggling as these structures are, they're still just part of the observable universe. What's even more mind-bending is the idea that the universe could extend far beyond what we can see. The observable universe stretches 93 billion light-years across, but it's possible that it's far larger than we can detect. In fact, the universe may be infinite, stretching endlessly in all directions, with structures like superclusters, galaxies, and stars continuing to form and evolve beyond our observational horizon. These vast structures, though incomprehensible in their scale, are not just points of scientific curiosity. They are reminders of the incredible grandeur of the universe and our small but important place within it. We are just one tiny part of this cosmic web, living on a small rock in the Milky Way. Yet we have the ability to peer into the farthest reaches of space and uncover the secrets of the cosmos. The largest structures in the universe may seem beyond our reach, but they are not beyond our imagination. And as we continue to explore, our understanding of the universe's vastness will only deepen, further fueling our awe and wonder. As we zoom out and survey the grand architecture of the universe, we encounter the cosmic web, an intricate, vast network of galaxies, stars, and dark matter that stretches across the universe. This web is not random or chaotic. It follows a pattern that has been shaped by gravity and time. The cosmic web is the framework that underpins the large-scale structure of the universe, with galaxies clustered together in filaments, separated by enormous voids. These filaments are massive strands of matter that are connected by invisible threads of dark matter, which forms the scaffolding for the visible universe. We can think of the cosmic web like a spider's web, where the nodes represent galaxy clusters and the filaments are the threads connecting them. Just like a spider's web guides the movement of small insects, the cosmic web guides the motion of galaxies. The galaxies in the filaments are not static. They are constantly moving, influenced by the pull of gravity and dark matter. As galaxies move through this vast network, they are drawn toward the nodes, where the largest clusters of galaxies exist. This structure is so massive that it spans across billions of light-years, stretching far beyond the limits of our comprehension. Dark matter the mysterious substance that makes up about 27% of the universe's mass, plays a crucial role in the cosmic web. Although we cannot see dark matter directly, its presence is inferred from its gravitational effects on visible matter. It is the dark matter that holds galaxies together, prevents them from flying apart due to their high velocities, and gives the cosmic web its form. Without dark matter, the gravitational pull between galaxies would be insufficient to form these large structures. In a sense, dark matter is the silent architect of the universe, shaping its grand design without ever being visible to our eyes. The discovery of the cosmic web and dark matter has revolutionized our understanding of the universe. For centuries, we thought that galaxies were isolated entities, but the cosmic web has shown us that they are interconnected, forming a vast and cohesive structure. The space between galaxies, once thought to be empty, is actually filled with dark matter, guiding the motion of galaxies and keeping them in place. The universe is not a collection of random points in space. It is a unified whole, a giant interconnected system where every galaxy is linked to others through the fabric of dark matter. One of the most exciting aspects of studying the cosmic web is that it allows us to trace the history of the universe itself by looking at the large-scale structure of the cosmos. Astronomers can map out the evolution of galaxies and the forces that have shaped them over billions of years. They can observe how galaxies have been pulled together by dark matter, how they've collided and merged, and how the universe has expanded and evolved over time. This study of the cosmic web is like reading a map of the universe's past, giving us clues about its future. Yet, as much as we know about the cosmic web and dark matter, we are still just scratching the surface. The true nature of dark matter remains one of the greatest mysteries of modern science. Scientists are actively searching for ways to detect dark matter directly, using advanced particle detectors and space-based telescopes. If we can unlock the secrets of dark matter, we will not only understand the structure of the universe more deeply, but we might also gain insight into the very fabric of reality itself. The cosmic web and dark matter remind us that the universe is far more than what we can see with our naked eyes. There are vast, invisible forces at work, forces that shape the structure of galaxies, stars, and even entire superclusters. And as we continue to explore this invisible universe, we are sure to uncover more profound secrets that will challenge everything we think we know about space, time, and the nature of reality. As we look further into the vastness of space, we encounter the concept of the cosmic horizon, the limit of the observable universe. This horizon marks the furthest distance we can see, or, more accurately, the farthest light that has had enough time to reach us since the beginning of the universe. The universe has been expanding since the Big Bang about 13.8 billion years ago, and the farther away an object is, the longer it takes for its light to reach us. As the universe expands, objects that are farther away are receding from us, and light from those objects takes longer to travel to Earth. This expanding universe creates a cosmic horizon, a boundary beyond which we cannot see. This boundary isn't a physical edge or wall, but rather the limit of our observational reach. It marks the farthest point in space from which light can have traveled to us within the age of the universe. The distance to this horizon is approximately 46 billion light-years. That means we can observe objects up to this distance, but anything beyond that is effectively unreachable for us, at least with current technology and within the lifetime of the universe. Beyond this cosmic horizon lies an infinite universe. As the universe continues to expand, distant galaxies are being carried further away, and light from these galaxies will never reach us. This means there are regions of space that are, for all practical purposes, beyond our reach forever. Even if we could travel at the speed of light, there are areas of the universe that are so far away that the expansion of space would carry them out of our observable reach before we could ever get there. It's as though the universe is constantly slipping away from us, making it impossible to ever fully explore. This realization, this concept of unreachable space, can be deeply humbling. No matter how advanced our technology becomes, there will always be regions of the universe that are forever beyond our grasp. It's a sobering thought, but it's also part of what makes the universe so wondrous. The unobservable universe represents the unknown, the mysteries that we may never solve, the regions of space that will forever elude our exploration. The further we reach, the more we are reminded of how little we truly know. Yet, despite the vastness of the universe and the limitations of our reach, the human desire to explore remains undiminished. Every new discovery, every breakthrough in technology allows us to peer deeper into the universe, to push back the boundaries of what we thought was possible. We may never reach the edge of the observable universe, but every step we take in, understanding the cosmos, brings us closer to a greater appreciation of our place in it. The cosmic horizon is a reminder that in the grand scheme of things, we are but a tiny part of a much larger reality. But it is also a reminder that curiosity and exploration are not bound by limitations. Even though there are parts of the universe that are unreachable, we can still continue to explore, to learn, and to appreciate the profound mysteries that await us in the vast expanse of space. As we stand on Earth, contemplating the immense scale of the universe, it's hard to shake the overwhelming realization that the vastness of space defies comprehension. The distances between stars, galaxies, and cosmic structures are so immense that they challenge our very concept of measurement. And yet, despite this, we are driven by a relentless curiosity to understand, to explore, and to make sense of it all. The scale of the universe is not only difficult to grasp, but, in some ways, impossible to truly comprehend. Every time we think we've understood the distance to a faraway galaxy, we find that the universe stretches even further, further than our instruments or our imaginations can take us. The universe is infinite in both time and space, and it will always extend beyond the furthest boundaries of our perception. Consider this: the observable universe stretches about 93 billion light-years in diameter, a mind-boggling figure that we can barely begin to conceptualize. But that's just the observable part. The universe could very well be vastly larger, extending far beyond what we can see. And yet, there are limits to what we can ever know. As the universe continues to expand, there are regions of space so distant that they will forever remain out of our reach. The expansion of space itself means that some galaxies are receding from us faster than the speed of light. And the light from these galaxies will never be able to reach us, even if we wait for billions of years. What's even more perplexing is the idea that, given the immense size and age of the universe, the light we see from distant stars and galaxies is from a time long past. When we look at the most distant galaxies, we're looking not at where they are now, but where they were billions of years ago. The universe is not only vast in distance, but it's also vast in time. What we observe in the present is a reflection of the past, a snapshot of a moment that may have long since passed. This paradox of time and space, the idea that we are forever looking into the past, while attempting to understand the present and future, makes the task of exploring the universe feel like a never-ending journey. Every discovery we make opens up new questions, revealing that there is always more to learn. The more we understand, the more we realize how much remains hidden, obscured by the very scale of the universe itself. The impossible scale of the universe can feel disheartening at times, but it also serves as a reminder of the infinite potential of human curiosity. We may never understand every corner of the cosmos, but we are driven to push the boundaries of what we know, inching ever closer to the answers that lie just beyond our reach. The scale of the universe may be impossible to fully grasp, but the pursuit of understanding is what makes our journey through the stars so meaningful. We are not merely observers of this vast, impossible universe. We are participants in the ongoing discovery of it. Each new piece of knowledge, no matter how small, adds to the incredible tapestry of understanding that humanity has woven over the centuries. And while we may never reach the limits of the universe, the fact that we are trying, that we are constantly reaching, learning, and exploring is what defines us as a species. The scale of the universe may be impossible to fathom, but our determination to understand it is what continues to fuel our quest for knowledge. The universe is vast, and it will always remain beyond our full comprehension. But the journey to understand it is one we must continue. As we reflect on the overwhelming scale of the universe, it becomes increasingly clear that there are limits to what we can truly know. The universe is so vast, so complex, that even with the greatest minds and the most advanced technologies at our disposal, there are aspects of reality that will always remain beyond our grasp. But this should not discourage us. Rather, it should inspire us to embrace the mysteries that remain unsolved, for it is the very act of questioning and seeking that defines human progress. In the face of an expanding universe, the more we learn, the more we uncover new layers of mystery. The more we explore, the more we realize that there is always something beyond the horizon of our understanding. It is this constant push against the boundaries of knowledge that has driven humanity's greatest achievements, from the first steps on the moon to the discovery of the Higgs boson. But each of these discoveries opens up even more profound questions, reminding us that the universe is both a puzzle and an infinite journey. The cosmic horizon, the furthest we can observe, will always be the edge of our reach. Even with more advanced telescopes and instruments, there will always be regions of space that are beyond our observational capacity. The universe is expanding at an accelerating rate, and as distant galaxies move further away, their light becomes stretched and redshifted until they are effectively out of reach, fading into the void. While we can study the universe's past and observe its present state, the future of the universe, what lies beyond the reach of our telescopes and instruments, is unknowable, and yet we persist. We seek to map the vast distances between stars, to understand the nature of dark matter and dark energy, to measure the distances between galaxies, and to uncover the secrets of cosmic time. We are explorers at heart, reaching out into the unknown, even though we may never arrive at the destination. The pursuit of knowledge is a never-ending process, a journey that expands the boundaries of human experience, even as it reminds us of the limits of what we can comprehend. But perhaps that's the most profound truth about the universe. It is both infinite and finite, both unknowable and observable. The limits of our knowledge serve as a reminder that there is always something to strive for, something just out of reach that continues to challenge our understanding. And it is precisely because the universe is so vast, so complex, and so full of mystery that it continues to captivate and inspire us. Our knowledge may be limited, but our curiosity is boundless. And that curiosity, our desire to understand, to explore, To ask the big questions is what keeps us looking up at the stars. Each discovery brings us closer to the heart of the universe, even as we are reminded of how much we still have to learn. The limits of our knowledge are not walls, but doorways, leading us to new questions, new explorations, and new adventures into the unknown. In the end, the true beauty of the universe is not in the answers we find, but in the endless pursuit of understanding. The cosmos will continue to stretch beyond the horizon, and we will continue to seek, to learn, and to wonder. Even as we reach the limits of our knowledge, the journey itself will always be worth it.